thank you for all you guys that are attending today. So with that said, let's jump into the content. Before I do that, let me introduce myself. So my name is Terrence Smith. I lead the team of commercial technical application engineers for GE Grid Automation for North America. So this includes the protection and control team as well as the substation automation team. And I've been with GE since about 2008. Today, I'm going to talk about centralized protection. And so in today's agenda, what I really want to cover is some of the challenges, some of the unique challenges that occur with large switchgear lineups and how those challenges create issues for low impedance bus protection. And then I'll talk about what centralized protection is, what centralized protection looks like, and how centralized protection helps to solve some of those unique large switchgear lineups. And I'll talk about some of the future protection scheme solutions that can be available with this sort of architecture. So, before we get cranked off, let me talk about some of the challenges to big switchgear lineups and low impedance bus protection. Now, this presentation is about centralized protection. So I'm not going to spend a lot of time talking about low impedance bus protection. If you're lost at some point, you can go back, and we have several presentations on both low impedance bus protection, on process bus and 61850, which will both be keyed up to this presentation. So I would encourage you to review those tech talks or those resources from our resources page as well. In the limited time we have available today, we can't do a full refresher of some of those concepts. But if we talk about low impedance bus protection of switchgear, fundamentally, the nice thing and the reason we use low impedance bus protection of switchgear is that we can achieve operation of the protective device in less than a cycle, about a cycle. Now, part of the reason we can do this is low impedance bus protection is using, or low impedance bus differential, I should specify, low impedance bus differential. Low impedance bus differential is measuring the current into the zone of protection and out of the zone of protection. And so we have a defined zone of protection. So we don't have to worry about overreach like we do with the time overcurrent. And we don't have to worry about coordinating those times. So we can operate without any intentional time delay. Now, the reason that we want to do this for a large switchgear lineup, a large industrial switchgear lineup, is because we can operate in less than one cycle. So one of the things that does for you is that can lower your arc flash incident energy because we're operating faster. Now, remember that's one cycle for the protective device. You still have a 3-cycle or a 5-cycle breaker behind that for your total arc flash clearing time. I want to point that out. But operating in one cycle is a lot better than for a traditional time overcurrent where you might be into the seconds. So you can lower that arc flash incident energy. When you operate fast like that, not only does it lower the arc flash incident energy, but it's also going to lower and reduce the mechanical stress, electrical stress for those fault currents. So that's the electrical stress, the burning, that sort of thing for fault currents, but also the mechanical stress on your insulators for those bus faults. Unlike high impedance bus differential, where in high impedance bus differential we have to sum our currents external to the protective device, to the relay. So unlike high impedance bus differential, low impedance bus differential gives us lots of available forensic data if we have an event. And because we have all those currents, all the currents connected to a bus wired to that low impedance bus differential relay, not only does it give us forensic data, but it gives us a centralized device for a DCS system to poll for metering data. So it can become like a data concentrator for us, a data concentrator for those currents. Another nice thing about low impedance bus differential protection of switchgear is we can achieve less than a cycle of operation with an arc flash relay, with arc flash sensors that sense the light. But unlike arc flash sensors, bus differential will work even if we close into a bus that is grounded, that bus that has safety grounds on it. If you think about those safety grounds, those don't produce light. And if we close into safety grounds, we're not going to produce an arc flash incident, or we're not going to produce an arc or an arc flash relay to operate. Whereas a low impedance bus differential would definitely operate for that. So what this sort of does is it sort of makes the case for using low impedance bus protection of switchgear. Now, if we're using low impedance bus protection of switchgear, the natural next step to that becomes a centralized protection scheme, which we'll get into in a few more slides. But before we do, let's talk about how we do this inside of GE. The traditional way that we do low impedance bus differential inside of a GE relay is with either the B90 relay, that's the Bravo 90, or the B30 relay, the Bravo 30. Now, the UR relay, if you're familiar with the UR relay, is sort of a modular relay. And we can put different types of modules in the relay within a few exceptions. There's always real estate exceptions, right? So one of those exceptions is we can put no more than 3 DSP modules into a UR relay. Now, DSP stands for Digital Signal Processor. It's where we wire CTs and VTs. And one of those modules has, it's the 8N module. It's got 8 places to wire currents. So inside of a B30, we can wire the 3-phase currents at the top of that module and the 3-phase currents at the bottom of that module to give us 2 places to wire 3-phase currents on each of those modules. Since there's 3 modules in there, that gives us the ability to do a bus that has up to 6 breakers connected to it with a single B30 relay. Now, the problem that we encounter is that there are a lot of buses out there that have more than 6 breakers connected to it. So we need to be able to protect larger buses. And that's where the B90 comes in. The B90 is a UR relay just like the B30, but it's a little bit different variant than the rest of that protective relay family. And when I say it's a little bit different variant, what I really mean is the B90 is a phase segregated relay. Now, a segregated relay is a relay similar to the IACs or the older relays. There can be a relay per phase. So if I have 8 places to wire currents and 8 places to wire currents per module on the relay, and I can put 3 modules on the relay, that can give me the ability to protect a bus with up to 8 breakers connected to it with a single B90. Now, since it's phase segregated, I could protect even a bigger bus if I had an A phase relay, a B phase relay, and a C phase relay. So with 3 B90s like that, in that phase segregated arrangement, I can protect a bus that has up to 24 breakers connected to it. Now, a bus that has 24 breakers connected to it, pretty big bus. And that would cover most of the buses that we would find out in the wild. There's a few issues though, right? Most of our industrial switchgear lineups look like this bus to the left here, where we have breakers connected to a bus, and we typically have a tie. Now, 2 of those breakers on each side of the bus are going to be mains typically, but nonetheless, it looks like that. Now, for a big bus with up to 24 breakers connected to it, that might look like 4 relays there, 3 or 4 relays, at least 3 relays to do the 3 phases. If I need to do logic and share logic across those relays, I may do that with a 4th relay, like I show here. Now, the problem with that, there's a few problems with that. The biggest problem is that this can be a real estate problem. Now, if you've got a bus that's got 24 breakers connected to it, you could make the case that, yeah, you've got plenty of real estate to spare. But in most instances, that's not the case. You can have a real estate problem. So one of the challenges immediately that comes to mind is the fact that if we've got a big bus, we may not have the real estate to have 3 or 4 different relays to protect that bus. So let's talk about centralized protection, and then we'll talk about how centralized protection can help with these big switchgear lineups and what we can do with centralized protection. So what is centralized protection? This is an example of a centralized protection scheme. So in a centralized protection scheme, we're going to have a centralized device that is providing protection for the entire piece of equipment. And in this case, the piece of equipment is this entire distribution substation, at least the distribution substation between the low side of the transformer and all the feeders. The transformer in this particular case, because of the architecture I'm showing, isn't included inside of this centralized scheme. Could be, but for this particular one, it's not. So the reason I show 2 relays here is because we probably want to have some redundancy. If we're putting all of our eggs in a centralized basket, we probably want to have some redundancy with that. Now, this gives us something we've not had in the past. Typically at the distribution level, we don't have this type of redundancy. So, but since we've got fewer devices, we can have this sort of redundancy. The black boxes that are at each of the feeders, those represent merging units. And what a merging unit is it is basically a device that's going to have the currents and voltages wired to it, going to have statuses from each of the breakers, any alarms from the breakers, and then it's going to have output contacts to control the breakers, to trip and close them. And then it is going to publish the sample values from those wired CTs and VTs. It's going to publish the status and alarms that are wired to it to a network. And each of those blue lines right there represents a network. And in this case, since each of those blue lines goes from the merging unit to the relay, this represents a point-to-point network. Now, we'll talk about different network architectures and the pros and cons of each, but that's what I'm representing with this particular slide. So in this case, the relay is subscribing to those sample values, the currents and voltages that are wired to the merging units. It's making its calculations, and then it's making trip decisions or other control decisions, maybe close, and then it's going to publish a message to that network that can be subscribed to by the merging unit to operate the breaker. Now, in this case, we're not only doing bus protection of the bus there, but we're also doing the primary protection of each one of those feeders with those protection units. Now, the pieces that build this sort of system, the first one is the merging unit, which I just mentioned. There's two variants of the merging units that we offer. There's the MU320 and the MU320E, E standing for extended. So extended has a little bit more I/O capability than the standard MU320. Unique to the MU320 is that it can be wired up to two sets of currents and voltages. So that's a total of 8 voltages and 8 currents that can be wired to the MU320, and it can publish both of those sets. It is connected through a network, either a point-to-point network or some sort of switched Ethernet network, or maybe even an HSR network, to a process bus module. Now, remember I said earlier when I was talking about the B30 and I was talking about the B90, remember I mentioned that it was a modular relay. So the module that I show here is a module that exists inside of that UR relay. And specifically for this centralized protection scheme, it is the B30 relay. So those connectors that are shown on that module, those are fiber optic connectors. And those connectors, there's 8 of them shown there. They can be either connected to a switched Ethernet process bus, or they can be connected to individual merging units in a process bus network. So that's up to 8 different merging units. So let's take a look at what that module looks like. As I said, there are up to 8 of these ports. These are fiber optic Ethernet ports on the back of the relay. There's a few different variants of this particular module. And this module that we show here is the module that you would typically purchase if you were purchasing your UR relay, if you were using a point-to-point physical architecture, because it's got up to 8 ports. If you were connecting to a switched Ethernet network, you'd probably only need 1 port, or you'd really need 2 if you wanted to do 2 ports. So using those ports, the relay can subscribe to the sampled values from the merging unit. It can subscribe to goose messages, which are peer-to-peer messages from the merging unit for those alarms and for the status of the breakers. And then it can publish a goose message to that same process bus network. And that published message can be a command to either trip or close the breaker. The merging unit, again, will subscribe to that message and operate its output contacts. One of the key things, especially for a process bus network like this, though, is that we have to be able to sync our signals. And what you didn't see on the previous slide was a clock source to sync those signals. And part of the reason I did not show that clock source is because the UR relay through the process bus module can be a master clock in a precision time protocol architecture for the process bus network. So the relay itself can be a master clock for all of the merging units that we saw on that network. So let's see what the back of the relay would look like when we do this. So here's our process bus module. This is that same module that I just mentioned. It's got 8 fiber optic Ethernet ports on it. That would be connected to either 8 individual merging units, or it could be connected in a switched Ethernet process bus 2, which is also connected to merging units. And then this would reduce wiring significantly. So we can, as you can see, this relay is fully configured. The only wiring that's required on the relay is, in addition to the fiber optic connectors, is the grounds and the power supply. So not only do we reduce our labor costs on the process bus and wiring, we reduce the cost in documentation and prints and the time. The biggest thing is that we reduce the time, and this can be more reliable. The other Ethernet port that we show there is the station bus. Now, in our centralized protection scheme that we're describing for a large switchgear lineup here, that station bus would be used for it would be the connection to a DCS system. We'll talk more about that in a few moments, but that's what we're going to use that other Ethernet port for. So that's what the back of the relay looks like, and this is what a merging unit could look like. This particular merging unit is in an outdoor cabinet out in the yard. Now, the merging unit itself, it can be connected to a switched Ethernet process bus. It can be connected to in that case, it would be connected to a switch. It can be connected point to point to the back of the relay, directly to the back of the relay. Now, the MU320 there, it supports addition to a 61850 and can do 61869 or 61850-9-2 LE. The other piece of this is it can subscribe to the time signal from the UR relay. Now, I show this particular merging unit here out in a cabinet out in the yard. If we're doing this in a large switchgear lineup, this would be in either the low voltage compartment for the switchgear or somewhere close to the breaker, so that it could be wired to the CPs from the medium voltage breaker and wired to the trip and close signals for the trip and close contacts for the breaker, and also have the breaker status fixed to a finger, the truck contact, any other alarms that are on the breaker wired to its contact inputs. Okay, so let's look at what these topologies look like. So here is a point-to-point topology. So I've got 8 merging units in this particular distributed topology. Now, remember, I'm limited to 8 if I'm using a point-to-point topology, because that's the maximum number. I'm limited to 8. That's the maximum number of ports I can have on the back of the relay, the maximum number of ports. But with those 8 ports and those 8 merging units, since each merging unit can be connected to up to 2 sets of CTs, I can have currents wired from 2 sets of breakers. So for this particular scenario, or this particular architecture, with those 8 merging units, I can protect up to 14 feeders. Now, the other 2 currents that are left over, those are each connected to a CT from the tie there. So that takes up all 16 of the currents that I have available. So what I can do with this particular topology, with this point-to-point topology, I could protect a bus with up to 14 feeders connected to it with a single B30 relay. That solves a lot of my real estate problems. And as I get into a centralized protection scheme where I'm going to do the overcurrents for those feeders as well, it can solve some other problems for me as well. The second network that we can talk about is a PRP network. So a PRP network is a switched Ethernet network. So what I show there is I've got 2 switches there, and each of those switches is connected to each of the merging units, and it's connected to the B30 relay. Now, the reason I show two switches, not because I have to have two switches, is because I'm using a PRP network. So PRP stands for Primary Redundancy Protocol. And basically, these two networks are working in parallel. So whatever signal arrives first is basically the winner, and there is zero failover time if one of the switches should fail. This gives me some redundancy of my network. The B30, that would only require 2 ports on it, and each of the MU320s would each go to a different switch. Or, excuse me, each of the MU320s has 2 ports on it, and each of those ports would go to a different switch in this primary redundancy protocol. So based on that, our limitation isn't the number of ports on the back of the relay, it is a limitation inside of the relay itself. So we can connect up to 24 merging units here, but at 60 hertz, which here in the United States, what we're really going to be looking at, we can do up to 21 feeders. Now, if we're in Europe, I know there's a few Europeans that have joined us. At 50 hertz, we can do up to 24 feeders. The last type of network that I should mention is, an HSR network. Now, HSR, the H and the S do not stand for high speed. Right? HSR stands for high availability, seamless redundancy. And basically what we would do in an HSR network is we build a ring of our merging units and relay. So a fiber optic port goes from the B30 to the first MU320, out of that MU320 into the next around the ring, all the way back to the B30. Now, since this is a ring, it gives us some redundancy without the added cost of having switches. In the MU320, we would also have to have, the UR supports this sort of ring network. The MU320 would have to have a separate device called a red box to provide this HSR ring. There are some maintenance issues with the HSR ring that I don't particularly like. I think this is not an optimal architecture, so I typically don't mention this very much. The things that I don't like about the ring is if I take one of the merging units out, I've broken the ring. There's some other issues. Each one of those hops causes a little bit of latency, and that's another thing that I don't like about it. But still, it is an available architecture. So that's what centralized protection is. Let's talk about how centralized protection could help. So when we look at centralized protection and how centralized protection helps, the biggest thing is if I have a large switchgear lineup, the only thing coming across shipping splits is a fiber optic connector. So what that means is the only thing that's coming across the so if I put my MU320 in the breaker compartment close to the breaker, the only thing that has to come across a shipping split is that fiber optic connector. So what that means is that can make my installation time of that large switchgear much faster. The other thing is that since the feeder protection as well as the bus protection are in that B30, that cleans up my complete protection and control solution. Also, since my B30 is no longer, since I don't have discrete relays that are in each compartment, I'll only have that single B30, and that B30 has everything wired to it. It can become a single device that can act as a communications concentrator or a data concentrator. So if I have a DCS system, that one DCS system can control the entire switchgear through that one relay. Or if we need to have redundancy, it can control it through the two relays. The other piece of this is, since my CTs and VTs and my trip and close signals are coming across a fiber optic network, there's no reason for me to have the protective relay or any of the control devices in close proximity or inside of the arc flash boundary. So I can move my protected devices outside of the arc flash boundary and move those into a near gear panel, a near gear HMI, or at the very least have it on the gear but outside of the arc flash boundary. That moves all of my operations personnel, when they're operating the devices, outside of the arc flash boundary. And again, since this one device is controlling everything, it's one device for my DCS system to interface with. It also makes having a near gear HMI to do my control a little bit easier and a little bit cleaner solution. And then another function that is available to us is, since all of my signals are in a single device, it allows me to unlock new protection schemes. So when I say about what I mean by new protection schemes, is it makes it very easy and very simple to use zone selective interlocking schemes between the feeders. It makes it very easy to do other protection schemes that would have been more complicated to share across multiple discrete relays. Having one central relay for a switchgear or a substation, in this case, I'm showing it for an incomplete substation, because in the case that I show in this slide, not only were we doing the protection for the large bus, but we're also doing the transformer protection for the incoming feeders through a centralized protective relay. In this case, this would be a B30. But this sort of shows the functionality of having a near gear HMI and having a single device for the DCS system to interface with. By having a near gear HMI, I can do all of my controls. I can do all of my controls in a near gear HMI that is interfacing with the B30 relay. So what that means is I can have a single line that shows the layout of my gear. The operators that are operating on that HMI can be outside the arc flash boundary, and they can trip and close breakers from there. I can have alarm pages from that same HMI. So I can have annunciator type alarms that show the alarms and what the condition is of my breakers. On top of that, I could use that near gear HMI to do trending. I could do that trending in the relay, or I could do it with the HMI so that I could have trend reports of current, voltage, power, that sort of thing for my switchgear. And then lastly, I can have that near gear HMI type scheme automatically download waveforms in the event that we have an operation of the B30 and get that information into that near gear HMI for analysis. Let's talk about future protection scheme solutions and current protection scheme solutions, okay? So if we think about a traditional system, the systems that we've always used, it's going to require to do the sort of protection that I showed on the last slide, where we're doing multiple feeders, we're doing a bus protection, and we're doing transformer differential. It's going to take multiple relays. So we're going to have F35s or an F35 to do the feeder protection. So that's going to give us our overcurrents, directional overcurrents, sync check, things like that we need. We'd need a transformer relay to do the transformer protection, and we would need a bus relay to do the bus protection. So as of the version 7.9 release of the UR, we added some centralized protection software options to the B30 that it can be ordered with. Now, 7.9 firmware was released in December of 2019, so this has been around for a year. We find ourselves in December of 2020 finally. But there are three different variants, three different software options. The order code IM gives you 3 bus protections, and you can have 8 CTs plus 6 VTs. Process bus only, and it can do 8 feeder protection and control. So this is very simplified feeder protection and control. This would be overcurrent. The order code OF gives you 6 zones, but 16 feeders. So I can do 16 feeders protection and control. Process bus only again, and I can do 16 VTs, I can do 16 CTs and 6 VTs. The real centralized protection variant is the multi-feeder IY. Now, what IY will do for us is it will give us 3 zones of bus protection, and it will give us 6 feeder PNC. And with this one, not only do we get the overcurrents that we get with the previous 2 software options, but we also get directional overcurrents. We get a frequency elements. We get sync check, and if we need it, we can get 79 for an overhead distribution substation. In our scenario here, when we're talking about a large industrial switchgear lineup, we really don't need 79. Plus, we get multiple overcurrents per feeders. And in this scenario, we can do 8 CTs and 4 VTs and then process bus. The plan is to have a 30 variant that will do up to 16 feeders PNC, 2 transformers, and it will do the 16 feeder protection like the IY does the 6. So it will have the directional elements, that sort of thing. But it will also incorporate 2 transformers. And this is process bus only, but it'll do up to 24 CTs and 24 Cs at 50 hertz, 21 at 60 hertz, plus 6 VTs. So that's planned for a future of the B30 in the somewhat near future. So, in conclusion, I'll say centralized protection is available today. It can help solve challenges on some of these large switchgear. Specifically can help solve some of the challenges around arc flash incident energy and some other protection challenges. Process bus is the key enabler of these centralized protection schemes. And these protection schemes can solve some installation challenges, speeding, commissioning, and installation, and installing switchgear faster and better. Okay, so one of the questions that we have is, how do we have redundancy on a centralized scheme? So a lot of that will depend on your architecture. So it will depend on your architecture and your philosophy. So it's easy to have 2 relays, right? So if I have a point-to-point network, what that would look like is the MU320 has 2 fiber optic ports on the back. Each one of those fiber optic ports goes to a different centralized protection relay. In a switched Ethernet process bus, what that looks like is each of the centralized protection units, each one of the B30s, is connected to the switched Ethernet network. and they're subscribing to all the MU320s. So centralized protection redundancy in these centralized protection schemes is actually easier to achieve than the redundancy that we would need on a traditional process bus scheme. Now, the other piece to this too is that at the distribution level where we're talking about medium voltage distribution, we've never had any sort of redundancy before. And we can very easily achieve, at the cost of just another relay, redundancy with one more relay versus, if we had to have redundancy on a bus that had 10 breakers on it, it would cost us 20 relays versus 10. This would cost us 2 relays versus 1 to have redundancy. So redundancy is probably a good idea in this sort of scenario because we're putting all of our eggs in one centralized basket, but it's not like the costs that would be required for redundancy at the traditional approach. It also it's also going to be a little bit easier to implement and achieve. There's a question here about communications requirements for next generation equipment. So I would say if you are looking at the requirement that you want on your protection and control IEDs, at a minimum, you should look for 61850, the protocols of 61850, both station bus, goose messaging basically, report control blocks through MMS, and process bus, either 61869 or 61850 9-2LE as a requirement for your system. Now, all of those protocols are Ethernet based, so that means that your physical architecture needs to be Ethernet. How is the performance of centralized versus traditional? And so when I see the word performance there, what that immediately brings to my mind is what is the latency of your centralized scheme, your process bus scheme. So what do I mean by latency is there an additional time adder on the process bus versus a traditional output contact or a traditional wired solution? There is a small adder. Usually that is around 4 to 5 milliseconds. Now, as it turns out, 4 to 5 milliseconds is a typical time for a mechanical output to operate on a relay. So if you replace that mechanical output on the merging unit with a high-speed output, so this would be an electronic output, those are available on the MU320 now as an option. If you do that, you get back that 4 milliseconds. And so you come back to about the same sort of performance with the high-speed outputs as you would a traditional relay with a mechanical output. Do I think that question is, do you think centralized will be applied on high voltage transmission in the near future? And I suppose the key to that, the answer to that question will depend on your definition of near, right? There are some challenges to transmission that make centralized a little bit more challenging than it is for distribution. So in distribution, we can sort of know what our architectures look like. They look like bus with a bunch of feeders off of it. In transmission, we can have multiple bus arrangements. And so those multiple bus arrangements will require multiple different types of protection architectures. And so because of the variance that you might see in transmission, I think that distribution will come first? And again, the answer to that question really depends on what your definition of near is. And I'm not sure how to define the near future, so I'm going to leave my question as I just answered it. Next question I see here is, how many zones can be accommodated with the B90? So with a traditional B90 relay, we can accommodate up to 6 zones of protection. Okay, yep, so here's a question. Do merging units require a separate GPS? So I hope I addressed this question during my presentation, because I hope that I very explicitly explained that the UR relay itself can be the master clock for the process bus network. If it is the master clock for the process bus network, the merging unit does not need a separate GPS. So it would not need a separate GPS. So here's a question. What are the distance limitations between the merging unit and the central protection relay? Typically, well, on our relays, the Ethernet connection between the relay and the merging unit is a fiber optic Ethernet. So if we go a point-to-point between the relay and the merging unit, there is a dispersion limit of the fiber, right? That dispersion limit, I am not 100% certain of the MU320. I remember from our brick product, which has a similar transceiver on it, we could go up to 500 meters before we had problems with that dispersion limit. If we're going from a switch to a Ethernet network, as long as we supported that Ethernet network, we could have a lot more flexibility on the actual distances. What is the cost comparison for a centralized unit compared to having individual 850 feeder protection relays? So that's a question that always comes up. It's a cost comparison. As I look at this, you have to buy the MU320, you have to buy the B30s. The cost of the hardware costs will be similar between the two, especially if you're comparing an 850 to an MU320. They will be similar. The real cost savings comes in the labor savings at site, wiring across shipping splits. And the cost saving comes in, having fewer devices to engineer and fewer devices to set. Okay, I think I addressed that question. Can the merging units have current and voltage displays? That's a fascinating question. It gets into a philosophical problem for me. So our merging units do not have current and voltage displays. They don't have them. Philosophically, I would think that we should not have displays on the merging units, because that display would really only be used during commissioning, and it would cost us money. My personal vision of merging units is that merging units will become more of a commodity type item. So when I say commodity type item, is that we will do things to drive cost out of them. So it doesn't really give a lot of benefit to having those displays on the merging units, and it goes in the opposite direction that I personally think merging units should go. Why do we have a difference of the amount of feeders that we can protect with the B30 with a PRP topology between the 50 and 60 hertz frequency? Is this due to limitations of the CPU? Yes. So the limitation, yeah, the limitation is really that 50 hertz is slower. So you have a slower sample rate. If you have a slower sample rate, you have more time to turn those samples into a phaser. So that is the reason that you see a different number of feeders that you can protect or connect to with 50 hertz versus 60 hertz. Okay, so here's a question. How are these merging units different from the brick product that I heard of? The key difference is that the brick could only do, it was a GE implementation of 61850's process bus requirements. So it was a GE requirement. It's a very important question because the process bus implementation that I talked about today with the MU320 and the process bus module is using 9-2 LE. Now, both 9-2 LE, or it can also use 61869, but both of those, as well as the brick, were defined by the 61850 standard. The difference between the brick solution and the 9-2 LE solution, for example, is that multiple vendors have implemented the 9-2 LE solution. So that makes it much more universally accepted. In other words, you would not have to be stuck with one vendor if you're using a 9-2 LE implementation versus an implementation that just one vendor has chosen. Another question I see here is, won't the B90 be used for centralized protection? Right now, we're using the B30. The reason for that is, as I mentioned earlier, the B90 is a phase segregated relay. So it operates per phase, whereas the B30 can operate like a traditional UR relay. So that's why I'm talking about the B30. That's why we've implemented the B30 as our centralized protection relay. How does individual feeders protection outage managed when using a single relay to protect multiple pieces of equipment in the substation? So I think that really comes down to the point of you probably will want some redundancy in your centralized scheme. So again, that's fairly easy to implement in either a point-to-point switched Ethernet process bus or even a HSR ring, because you've got one relay there that you need to have redundancy for. Okay. Yeah, so I think I've got time for this last one. So if I didn't get to your questions, I apologize. But this last one is, you mentioned that you didn't like the ring configuration. I did. Of the centralized relays because you could break that ring. If a ring sector is lost, you would still have connections from the two adjacent centralized relays, wouldn't you? Yes, you're correct. So if you lost a part of the ring, so if you lost one of the MU320s, for example, you would still have the other way around the ring. So you would not lose, which is the beauty of this sort of ring network, in that if you lose a section, you still got communications. You just no longer have the ring. The problem that I have with the HSR is that it does add some latency. It does add some latency for each individual hop around that ring. It's not much latency, but it does add some. The other problem that I have with, well, there's some other problems. The HSR ring does not give me a way to segment and control my network traffic like a managed Ethernet switch would. So that could cause me some problems. Another issue is if I want to maintain my ring or repair my ring, if I've lost one of my MU320s, what I end up having to do is, so if I have an a breaker section out for maintenance, it fails, whatever, and an MU320 is out, if I want to restore my ring, I have to plug each one of those. I have to have a female-to-female connector to plug the two fibers into. So it costs me a little bit of labor costs. So those are sort of the reasons I don't like the HSR ring. If I'm going to use a network, I would prefer to use a switched Ethernet process bus. Okay, Colleen, I think I am a minute over the hour. My apologies for going over. I'm sorry that I didn't get to everybody's questions, but hopefully we can address those through email. I'll turn it back over to you, Colleen, for your concluding remarks.
Thank you so much, Terry, and thank you everyone for attending. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful day.